Let P, Q, A and B be real numbers. Part A. Show that 1 over root P minus root Q equals root P plus root Q over P minus Q, and state suitable restrictions on the values of P and Q. This is a standard Surd question, and we do it in the usual way by rationalizing the denominator of the left-hand side. And to do that, we rely on the difference of two squares identity. We take 1 over root P minus root Q, and we multiply it by 1 in the form root P plus root Q over root P plus root Q. And now root P plays the role of X, root Q plays the role of Y, and so on multiplying the denominators we obtain root P squared minus root Q squared, which equals root P plus root Q over P minus Q, since root P squared is P, root Q squared is Q, as required. And now we have to determine the suitable restrictions on the values of P and Q. And to do so, we first consider the square root function, whose definition is provided here. The domain of the square root function, i.e. the numbers that we can put into it, are all of the non-negative real numbers. The range of the function, i.e. the numbers that come out of it, are also the non-negative real numbers. And the specification of the domain here tells us what we already know, that we can't take the square root of a negative number. And since we are dealing with an expression containing root P and root Q, we thus need both P and Q greater than or equal to 0, which is our first condition on P and Q. In addition, we note that P minus Q occurs in the denominator of the expression that we derived. Since we cannot divide by 0, we thus need P minus Q not equal to 0, and hence we need P not equal to Q, which is the second required condition. Part B. Use the rules of inequalities to show that if A is less than B, then A plus B over 2 lies between A and B. And this is a result that you should already know. It says that the average of two different numbers lies between both of them. We have to show this result by using the rules of inequalities for real numbers, and I've stated them here. Now, we should note that we in fact have to prove two different inequalities, namely A is less than A plus B over 2 and A plus B over 2 is less than B. And in fact this turns out to be quite straightforward. To prove the inequality on the left, we start with A is less than B and we add A to both sides. That simplifies to 2A is less than A plus B, and we can divide through by 2 because it is a positive number to show that A is less than A plus B over 2. To prove the inequality on the right, we start with A is less than B, and we add B to both sides. This simplifies to A plus B is less than 2B, and we divide through by 2 to find that A plus B over 2 is less than B. And now we combine the two separate inequalities into the single inequality A plus B over 2 lies between A and B, as required. Part C. Hence show that the square root of r plus 2 minus the square root of r lies between 1 over the square root of r plus 2 and 1 over the square root of r for r greater than 0. This is a hence question, so we have to use the result from part A and or the result from part B to show the result in this part. Now, it's far from obvious how we should proceed in this question, so what we shall do is to look for similarities between the expressions that we can use, i.e. those from part A and part B, and the one that we have to construct. So here is the expression that we have to construct, and here is the expression from part A. And we immediately notice that there is a similarity between the expression in the red box and the denominator of the left-hand side of the expression from part A. And it would seem that r plus 2 is playing the role of P, r is playing the role of Q. And so perhaps it's a good idea to set P equals r plus 2, Q equals r, from which we find that P minus Q equals 2. Now we note that the denominator of the expression on the right-hand side from part A is P minus Q, and so that denominator must be 2. Here is the expression from part B, and we note that the denominator is 2. That would suggest that A plus B is playing the role of root P plus root Q, since we know that the denominator of the expression from part A is also 2. So bearing in mind that P minus Q equals 2, i.e. P is larger than Q, then we should set A equals root Q, B equals root P, since A must be smaller than B. And then the inequality from part B becomes root P plus root Q over 2 lies between root Q and root P. And bearing in mind that P equals r plus 2, Q equals r, then on making those substitutions we obtain the square root of r plus 2 plus the square root of r over 2 lies between the square root of r and the square root of r plus 2. We now recall that the expression in the blue box is in fact the right-hand side of the expression from part A, and so we can replace it with the left-hand side of the expression from part A. And on doing so, we obtain this inequality, which looks very similar to the expression which we have to derive. But it's not identical because the expressions are inverted and the inequalities are going the wrong way. Can we fix those problems? Now we've derived this expression, but we want this expression. Before we go any further, we note that we can split this double inequality into two separate inequalities. And for both of these separate inequalities, we want to invert the expressions and reverse the direction of the inequality sign. And we can do both of those things at the same time due to this fact. If A and B are positive and A is less than B, then 1 over B is less than 1 over A. And on applying that fact to the inequality on the left-hand side, we find that root r plus 2 minus root r is less than 1 over root r. And on applying it to the inequality on the right-hand side, we find that 1 over root r plus 2 is less than root r plus 2 minus root r. And now we combine these two inequalities to find that root r plus 2 minus root r lies between 1 over root r plus 2 and 1 over root r, as required. And finally, we should note that we need r to be positive, otherwise 1 over root r is not defined. Part D. Given that 31 times 33 equals 1023, use the result from Part C to show that the square root of 1023 lies between 31 and 61 over 62 and 31 and 65 over 66. From Part C, we have this double inequality, and we must show this inequality given that 31 times 33 equals 1023. Now we see that 33 equals 31 plus 2, so it makes sense to set r equal to 31, r plus 2 equal to 33. And then we can substitute those values into the inequality from part C to show that root 33 minus root 31 lies between 1 over root 33 and 1 over root 31. And if we compare this inequality with the one that we have to show, then we see that there are too many square roots. And the obvious thing to wonder is, can we square them away? because that would make the two inequalities more similar. And the answer to that question is yes, due to this fact. If a and b are positive and a is less than b, then a squared is less than b squared. And then we could ask the question, does it help to do so? Well, we don't know for sure. We'll just have to see. So we start with the inequality that we have derived, and we square each quantity. To obtain root 33 minus root 31 squared lies between 1 over 33 and 1 over 31. And we can FOIL out the expression in the blue box to obtain this. And now we recall that root a times root b equals root ab, and we apply it to the expression in this blue box to give 64 minus 2 times root 31 times 33 lies between 1 over 33 and 1 over 31, where we have also added 33 and 31 from the previous expression. And on recalling that 31 times 33 equals 1023, we obtain these inequalities, which is beginning to look somewhat similar to the inequalities that we require. But we want inequalities involving root 1023, whereas we have inequalities involving minus 2 root 1023. And we see that we have a sign difference, so we have to multiply through by minus 1, which of course means that we have to flip the inequality signs. And on doing so, we produce these inequalities, which we can divide through by 2 to produce these inequalities. So we have inequalities involving root 1023 minus 32, and we can remove the minus 32 by adding 32 to every expression in these inequalities. And when we do so, we find that root 1023 lies between 32 minus 1 over 62 and 32 minus 1 over 66. And on simplifying, we find that root 1023 lies between 31 and 61 over 62 and 31 and 65 over 66, as required. And it's interesting to note that this is a pretty good approximation. The upper bound differs by no more than 4 ten-thousandths from root 1023. The lower bound differs by no more than 5 ten-thousandths. In this problem, we relied on this fact, that if a is less than b and both are positive, then a squared is less than b squared. And here is a simple proof using the rules of inequalities. If a is less than b, then on multiplying both sides by a, we obtain a squared is less than ab. And if a is less than b, then on multiplying both sides by b, we have that ab is less than b squared. And on combining these two results, we find that a squared is less than ab is less than b squared, so a squared is less than b squared.